Okay, so today I helped several people out with a couple of the difficult questions on the problem set. And the one in particular that I'm going to kind of walk through today, or tonight anyways, is the basketball jump shot. So I know I'll probably have to answer a couple more questions on this tomorrow, and I thought if I don't get to you, this is at least a way that you can look and follow along with what I'm going to say anyways if I sit down to help you. All right, so the basketball jump shot problem is probably the hardest one on the entire problem set. And the reason why is because they only give us a couple of things. They're only giving us the angle at which this is going to take place and the range of the shot. Now, I'm going to actually go ahead and get kind of a PowerPoint started here. And I'm going to pick some colors to work with. Alright, so if I'm going to sketch a picture of the basketball shot, I know that I've got my basketball player. My basketball player is essentially shooting a jump shot, so we're up in the air here, and our ball is right there, and we're shooting our jump shot, and the ball is actually at the same height as the goal, or the basket. Okay, so here's my basket, and this is like a 10-foot high goal, so obviously my player's jumping in the air and they just happen to keep the ball at that point. Now again, the ball itself is going to follow a trajectory that's going to be parabolic to go in. Now the things that I know, again, I'm listing the things that I know. I know that the distance in between here and here was 16.5 meters, so they gave me a range and they gave me an angle, and that angle here was 47.7 degrees. So again, these are the only two things that I know. Now I'm going to kind of walk through and review a little bit about what was the first thing that I did in the big problem of the day today. And the first thing that I did is I said, well, if I have a vector that represents a velocity, because that's what I don't know. I don't know this velocity. This velocity can be split up into its components. So I have a component in the x direction, and I have a component in the y direction. Okay? And for those of you that need to see the triangle, there's my triangle. Okay? Where this side is the same as this side over here. Now, this component, v of x, is just written as the v cosine of my angle. Okay, where this one is v of y is v sine of my angle. So again, I have my two components, and both of my components are written in terms of my v. Okay, and the v is what I'm looking for. Now just keep in mind that when we do these projectile problems, it's a story of what's going on in the x and a story of what's going on in the y. In the x direction, all the ball is doing is the ball is just moving across to the goal. That's all it's doing. There's constant velocity, which means that there's no acceleration. Okay? There's no acceleration that's going to take place. It's all constant velocity, which when we equate this into some kind of relationship, it just means that velocity is always going to be equal to a distance over time. Okay? It's that standard one. And if you're really confused and you're just looking at the very top equation, it's distance is equal to VIT plus 1/2 AT squared. But remember, there's no A. A is essentially 0. So this entire piece is disappearing, which this relationship right here is the same thing as that relationship. Okay? That's the only thing that's going on in the x direction. Now in the y direction, it's a different story. In the y direction, the ball, okay, has to go up, and then it has to come back down. Okay? And that's what it's doing. It's going up, and it's coming back down. So essentially, this is any one of our free fall type problems. Okay, it's very similar to something that's like free fall. We have a constant acceleration, and this constant acceleration is gravity, which means that A is equal to 9.8 meters per second squared. And that's what we're dealing with. All of our equations come out, so our D equals VI T plus 1/2 AT squared. Our VF equals VI plus AT, and our VF squared equals VI squared plus 2AD are the three equations that are up on the board that we're using. Again, because it's constant acceleration. So these are the three constant acceleration equations. Alright, so now back to our basketball player. They're going to shoot it. We know that part of the velocity goes this way, part of the velocity goes this way. The reason why it follows this parabolic curve is because both the things that are happening in the x direction and the y direction happen at the same time. Okay, that's the key. The key is that the x component and the y component are happening at the same time. Now in the x component, we refer to this as like our hang time. Oops. Hang time. It's the amount of time that it takes for it to get from here to here. In the y direction, it's half of that hang time. And the reason why is because we like to look at points like at the peak where our velocity is equal to 0. Okay? Because it's the time it takes to get to that peak, which means that we can then start to find things like initial velocities and final velocities. Okay? So we can start to look at our two changing velocities. So the time for the hang time is the time it takes to get to the top, and then the time it takes to get to the bottom. Okay, so the time to get to the top is half. If you want the full time, you have to multiply it by 2. So this time is half of the hang time. So typically what we do is we take whatever our time is and we double it. Okay? Because the time that we're interested in is the hang time, and the time over here is half of that hang time. Okay? So time is the thing that links them together, x's and y's. Now what we're going to do is we're going to start to examine what's going on with our ball in the y direction. Okay, so in the y direction, the ball is going up and it comes right back down. And we know that at the peak, there's a velocity that's equal to 0 meters per second. The starting velocity, whether it's when we throw it up or when it comes back down, is always going to be equal to that velocity that we figured out in the y direction from our components, or v sine 47.7. Okay, so now I have two velocities that I can deal with. I know that my acceleration is going to be 9.8 meters per second squared because I'm always working against gravity. I don't know my time, but remember that the time that I'm going to be interested in this is the time it takes for the ball to get to the peak, or the time that it takes the ball to get from the peak back down. And then I don't know my distance in the y direction, and the distance in the y direction is usually what we refer to as height. So our height is always the distance in the y direction. Alright, so now I've got these type of things, and what I'm going to do is I need to find a formula that relates these things together. If I'm going to treat this like a free fall problem, I like to do this. I like to take the point up here, which is my velocity where it's equal to 0, and I'm going to just drop it down here to this velocity. So I like to make this my initial velocity, and I like to make this my final velocity. So I have an initial velocity, a final velocity, I have an acceleration, I have a time. The equation that I like to pick is the middle one, because I want to find out this time. And time, again, is the key that links me back to my x. So my VF equals VI plus AT. And my VF is V sine 47.7. My VI is 0, and my A is 9.8, and I'm going to have T. Okay, so when I look at this right now, I can see that I have the V, that's what I'm looking for, and I see that I have the T, which is my linking variable. Because the T is going to be my linking variable, I'm going to solve for it. I'm going to get the T by itself. I'm going to divide by 9.8 on both sides. Now T comes out equal to V sine 47.7 divided by 9.8. Okay, so that's what my T is. But remember, this was the time to get from the peak to the bottom. I need to double this. Okay, I need to take this times 2. Now this represents hang time. Okay, I now have something that equates out into the time to get from the bottom to the top and back down. Okay, which is true of my entire trajectory, of my entire path. Alright, so now let's go to the x direction. So what's happening in the x direction? Again, the ball is traveling to the goal, and the only thing that I know is that I have a velocity in the x direction, I know that I have a distance, and I know that that time is important because time links me. And really those are the only three things that I can find on the x direction. Okay, because again this is a constant, there's zero acceleration, so I'm back to finding an equation that relates these. So again, my velocity is just equal to a distance divided by a time in a constant sense. So my V cosine 47.7 is equal to my distance divided by my time. Now, the time is on the bottom right there. I'm going to do a substitution. This is where I'm going to use some of those math skills that I've been learning. So my T here is equal to this fraction. I'm going to bring it back over here and put that under here for T. Now, because I have a fraction here and I have a fraction here, I'm going to multiply by my reciprocal. Okay? So in other words, my V cosine 47.7 is equal to 16.5 times my reciprocal, 9.8 over 2V sine 47.7. Okay? And I'll just double check. That was 9.8 2V sine 47.7. So I'm just multiplying by my reciprocal. Okay? Now all of a sudden I have just V's left. I want to get this V right here over here with this V. I'm going to multiply times a V. Okay? The V's cancel. If I do that to one side, I have to do it to the other. Now I'm going to get a V times a V, or I get a V squared. Okay? Still have the cosine 47.7. I'm now down to 16.5 times 9.8 over 2 sine 47.7. Now I got to get rid of this cosine 47.7, so I'm going to divide by cosine 47.7, which means I'm going to divide by cosine 47.7, and then I'm left with V squared by itself. Okay, to undo my square, I just take the square root, which means I just need to take the square root of this expression. Now, 16.5 is a number, 9.8 is a number. By the way, this would be in meters. This is in meters per second squared. That would give me meters squared per second squared. When I take the square root of that, that gives me my meters per second.